What is up, chumps? So today I'm gonna teach you about hash functions, what they do, and how they're used in blockchains or distributed ledgers to both create a cryptographic proof of work in proof of work blockchains, and also to compress the information you need to send across a network to validate a transaction. So first and foremost, a hash function is used to take any input data. This could be text, it could be a file, anything, it doesn't matter, and turn it into a fixed length string. Fixed length piece of zeros and ones to the computer. So that's what a hash function is. There are tons of hash functions, and they all have different pros and cons. One of the most common is SHA-256. Another one is Blake2. I know that there's like an MD, I think, as well. There's multiple hash functions, but they all perform the same purpose. And kind of each one has different pros and cons, again, to them, as far as like how fast they can move, the potential for what's called a collision. So when you're taking a hash function, you don't want one piece of data, or let's say I'm taking the hash of two files. I want it to be very difficult for someone to find another hash that would match my file exactly. This is because if I hashed my file, for example, and I put it up as an NFT or committed that hash to the Ethereum blockchain as an NFT so that people could validate that the file they received on the network, on IPFS or AWS, whatever, is the exact same file that was effectively stored on Ethereum, you need to use the hash function for that. So you take the hash of that file, you commit it to Ethereum. And that way I can validate that the file I'm getting from an NFT is the correct one. If it becomes possible or incredibly easy for people to fake that, to give you a fake file that has the same hash that was committed to the Ethereum blockchain, people can effectively, break your NFTs. They can substitute the real file for what they created that has the same hash that's on the chain. Luckily, this is insanely difficult, even in quantum computing. Most hash functions are quantum resistant, so that's very, very nice. Even if once we get to the point where there are quantum computers and they are really, really good at generating all these things, the hash functions that we have are still quantum resistant. So that is a hash function. You take a piece of information, you output a fixed length piece of data. And from here on out, I'm going to use SHA-256 as the example along with Bitcoin. So let's hop into this. All right, so we have, in a blockchain, we have blocks, right? Everybody knows this. Let's look at the anatomy of a block, the data structure that makes up a block. So every single block, except for the very first one, has three values. You have the previous block hash. You have the Merkle root, and I'll get to this in a second. Here's an example. And then you have what's called a nonce value. The previous block hash should be pretty self-explanatory. It's the hash. In Bitcoin, it's the SHA-256 hash of the previous block. The Merkle root is a hash of the information or the transactions that took place on that block or during that block. And then the third thing is the nonce, and this is where your cryptographic proof of work comes into play. The nonce is used by miners to change the data of the block so that they can find a hash, a SHA-256 hash of the block that begins with a certain number of zeros. This is the number of zeros required at the beginning of that hash is determined by the current hash rate of the network as a whole. This is so that it's not incredibly easy to find blocks. The goal is to create it in such a way that, for Bitcoin at least, it takes around 10 minutes to find the block or the hash of a block that satisfies the target, the hash target of 17 or 48 zeros, whatever the current difficulty is. So that's what the nonce is used for. The miners are randomizing repeatedly, millions of times per second, to try and find a nonce that satisfies the hash target, that creates a hash, a SHA-256 hash of the block that has that beginning number of zeros. So that's your cryptographic proof of work. It takes time to do that. The work required to make that happen, the number of transactions that are taking place, the electricity put into that work, that's your cryptographic proof of work. We're working under the assumption that it is difficult, excruciatingly difficult, just as it would have been with my file to find a similar hash, to find a hash, or a nonce, for the block, so that when you hash the block, it gives you that a hash that satisfies the network's target. So that's where your cryptographic proof of work comes into play. The next place where hashes are used heavily in blockchain is when you're storing transactions. When Satoshi designed Bitcoin, he wanted to make it easy, and indeed he needed to make it easy to validate transactions that have occurred on the blockchain. Bitcoin uses a technique called unspent transaction output to effectively determine how much Bitcoin you own. I'm not going to dive into unspent transaction output. It's called UTXO, but basically what it means is to determine how much Bitcoin you own, you have to sum up all of the transactions that sent you funds. And so you have the unspent output of each transaction. So in Bitcoin, when we're storing transactions, we store them in what's called a Merkle tree. This becomes incredibly valuable for UTXO because in order to validate, let's say, that you have the 5 Bitcoin you claim you have, I need to validate all of the transactions that you're referencing as, hey, I own this Bitcoin. And in order to do that, if we don't use a Merkle tree, I'd have to download the entire blockchain, right? I'd need to download every single block up until that point. I would need to download all of the transactions in each of those blocks so that I could create the cryptographic hash of them. Again, we're not trusting anybody here. We're working completely from, is the data valid? Is it valid? And if it isn't valid, then I need to reject this and find another node that is going to send me valid data. And so we're going to trust but verify, right? Where we can trust nodes to a certain extent, but we need to verify that what we're sent and what we've received is valid according to the rules of the Bitcoin protocol. So we've received information, and if we don't use Merkle trees, we have to receive the entire blockchain. And that is ludicrous. Like, that is so much crap. So what we're able to, with Merkle trees, what we're able to send instead is just Merkle roots. All we need to do is send the previous block hash, the Merkle root, and the nonce for every single block. And that's not that much information, honestly. That is very little information compared to all of the transactions that have ever taken place on the Bitcoin blockchain. That's a lot. I believe it's approaching 1 terabyte now. I don't want to need to download a terabyte of data. So we use Merkle trees. And we are able to validate using these Merkle trees. So let's say that I have one transaction on Bitcoin that proves that I have Bitcoin, right? So let's say it's just transaction 1. Ooh, my wife just sneezed. So we have this transaction 1, and let's say that it gives me, Sterling Long, 1 Bitcoin. And then let's say in the next block, I'm going to transact again. I need to provide a reference to transaction 1. And I need to effectively split the output or send it to whoever I'm trying to send it to. In order for the protocol to validate that transaction 1, the transaction I referenced, actually has the information that I say it has, and that it's part of the blockchain, the only thing a node needs to have is information up to this current block. And then they don't need to care about transaction 2, 3, or 4. All they need is the hash of each of those transactions. And then they can recreate this Merkle root and effectively validate this block. So when I send my transaction 1 in, the node takes that transaction and effectively recreates the Merkle root of that block using the transaction hashes that it may or may not have received from me or from another node. It doesn't necessarily matter. Well, I guess it does matter where they get it from. Again, trust but verify. You can get a lot of this information from many different sources, and then you can validate that the information is the same across those sources. So you have this transaction 2, 3, and 4 hash instead of all of the information that actually existed in the transaction. So we've effectively compressed most of this block into just 3 hashes. And then I send this reference to transaction 1, which is the transaction that has my data that I'm trying to use in this future block. So using all of this information, and in this data structure specifically, a node is able to validate my transaction without having all of the information of the blockchain readily available. So these are the 2 ways that hash functions are heavily used in blockchain to, 1, create the cryptographic proof of work, and 2, decrease the amount of information that needs to be sent over the network to validate transactions that are being committed to the blockchain. Both of these things are incredibly important. The cryptographic proof of work arguably is far more important than the network bandwidth usage, but both of them are required to make the network function smoothly, even with hundreds of nodes, like petahashes, petatera. Oh, I'm missing the word. Like insanely high hash rates for the entire network. You need to keep the amount of information that you're sending over the network minimalized so that the network doesn't get bogged down just by the number of messages and the amount of data it needs to send in the peer-to-peer network. So that's how hashes are heavily used specifically in Bitcoin. And most of the proof of work blockchains that you'll find will follow this paradigm, will follow this same block anatomy. They might have additional pieces, but they will have this previous block hash to create the chain. They will have this Merkle root, so you don't have to sync a ton of information across networks when people are trying to hop on board and begin validating transactions and essentially spin up their own nodes. And last but not least, they'll have this nonce so that they can create new blocks and randomize this value to create that cryptographic proof of work. So we have it. Hash functions, what they do, and how they work in blockchains. Thanks for hopping in today. I've really appreciated you joining me. If you appreciate this video, smash that subscribe button. I'm here to teach and help people understand how the technology that they use actually works at a foundational level.